Hello and welcome to my lesson. My name is Mr. Johnson. This is one of my 20-minute lessons for Satchel. I'm just going to share my screen with you, but today's lesson is entitled Electrons and Orbits and it forms part of the radioactivity unit for GCSE physics. Okay, so like I say, this lesson's about electrons and orbits and it follows on from the radioactivity unit. The whole point of this is to describe what happens when atoms absorb or emit radiation. By the end of this, you should be able to describe how and why the atomic model has changed over time, including reference to the Bohr model. Explain that electrons change orbit when there's an absorption or emission of electromagnetic radiation. And finally, describe how ionization occurs in atoms. So, if you've watched the previous lesson on this about atomic models, then you should, or even if you haven't and you've studied it, you should know the atomic model that we know and use today. Rutherford and his team proved that the atom was mostly empty space, but that there was a large concentration of positive charge at the center of the atom in a very dense but tiny mass, and this was the nucleus. As well as that, he proved that the electrons were outside the nucleus. Now, Rutherford didn't say anything about the energy shells. Rutherford's model just had the electrons in orbit around the nucleus, nothing to do with shells. It's a kind of cloud idea. And there was problems with that particular model in that scientists couldn't explain why those atoms, also why those electrons didn't collapse onto the nucleus and cancel out the positive charge, thus leading to the total destruction of the atom. Rutherford and his team assumed then that the electrons were around the nucleus in a sort of cloud of electrons. They didn't know about the energy levels or the orbits at that time. This couldn't explain then why the electrons just stayed where they were and why they didn't fall into the nucleus because of the force of attraction between them, causing the atom to collapse in on itself like a bit of a deflating balloon. How then did we fix this problem, and how do we then get to the modern modern atomic structure where we explain the arrangement of electrons in the atom? Well, it all started with observations. This is the want of science. We observe something and then we test what we've observed to see if we can come up with a working theory to explain the observation. Neon gas is an element from group 0 of the periodic table. It's also known as a noble gas. It's highly unreactive, and if we pass an electric current through it, it begins to glow orange. Different elemental gases also did the same, emitting different colors of visible light. Scientists at the time looked at the absorption and the emission spectra for these elements, and they found something odd about them. Now I've got neon's absorption and emission spectra on the bottom of the screen, and you can see for the emission spectrum, emission being the colors of light that is being produced or given out by the neon when it's glowing, and the absorption being the colors of visible light that neon absorbs when light is passing through it, you can see that there are marks in the same position on the emission and absorption spectrum, meaning that they were emitting and absorbing light at the same wavelength. If light was shone through a tube of neon gas, then the neon atoms would absorb some particular wavelengths of light, and these were the black lines on the absorption spectra, as shown here. The energy carried by light waves of these wavelengths was being absorbed by the electrons in the atom then. What was strange was that the specific wavelengths of light emitted by neon matched the same wavelengths of those that it could absorb. This was shown on the emission spectra for neon. And you can see that the colored lines here match the black lines on the absorption spectra, meaning that it's absorbing a wavelength of light and then emitting that same wavelength. So what's going on? Somehow, because the neon could absorb the same wavelengths and energy of the light that it could emit, and didn't absorb any of the wavelengths of light in between, it suggested that the electrons were at specific energies correlating to the wavelengths that were being absorbed away from the nucleus, and that they couldn't all just be mixed up in a cloud. It was the first time that scientists had evidence of this idea that the electrons were not just in one position around the nucleus of an atom, but were stepped in positions away from it, giving the idea of energy levels like rungs on a ladder. Now, Niels Bohr was a scientist who lived between 1985 and 1962. It was work of scientists like him that finally answered the question that we asked at the beginning of this. How did we arrive at this idea of energy levels? Bohr took the observations and suggested that the electrons were in energy levels or orbitals or shells. Bohr went further to say that the electrons could not exist at a position between those shells, and so they couldn't have energies between the energy required to be in that shell. By this, I mean they could have an energy that matched the energy level of a shell, but they couldn't have anything in between at all. So electrons couldn't exist between the shells. They literally had to be in a position on a shell and nowhere else. Finally, Bohr suggested that the color of the different gases in their absorption and emission spectra could be explained if the electrons in the atoms could move between the energy shells. And that's something that we're going to talk about in a moment. But quick question, what is the Rutherford model of the atom then? And how is Bohr's model different from the Rutherford model? Well, we've come across the Rutherford model before, earlier in the series or earlier in your revision. And the Rutherford model said that almost all the mass and all the positive charge in a tiny nucleus in the center of the atom and negatively charged electrons moved around the nucleus. Didn't say where, just said it was moving around it. Also said that most of the atom is completely empty space. The Bohr model amended that. It kept the Rutherford model, but amended the electrons. They can only move in specific orbits or levels around the nucleus corresponding to specific frequencies, and they can't exist anywhere in between. So that's our first outcome met. Describe how and why the atomic model has changed over time, including reference to the Bohr model. And now we're going to look at the next one. Explain that electrons change orbit when there is an absorption or emission of electromagnetic radiation. So how can an electron jump from one energy level to another? What will it need to make that jump? Well, as you can see from the GIF, something's required for that person to make the jump. And it's a similar sort of thing in real life as it is for an electron making a jump between energy levels. To go to a higher energy, it needs an input of energy. It needs energy to be delivered to the electron, so it gains energy to make the jump. It drops down again as it loses the energy it gained. In other words, it gives out or emits that energy so it can drop down an energy level. What happens then when blue light wave carrying energy is incident on an electron inside an atom? The electron absorbs that blue light wave. It absorbs the energy that's being carried by the wave, because if you remember your electromagnetic spectrum, waves carry energy, and that causes the electron to jump to the next energy level. We say then that the electron has become excited. The energy carried to the electron by the electromagnetic wave has a specific wavelength and energy. When the energy is transferred to the electron, the wave disappears. We can say that it's been absorbed. What happens then when the excited electron is present in an electron orbital? At this point, the excited electron releases the extra energy and drops down to a lower energy level. We say that it's become de-excited. In the process of de-excitation, the extra energy that the electron has now given up is carried away by an electromagnetic wave, and that wave has the same wavelength and energy as the one that was previously absorbed, meaning that the atom now glows with a specific color of visible light, in this case, blue, because that was the energy and the wavelength corresponding to the wave that was absorbed by the electron. The other thing is electrons don't have to jump by only one energy level at a time. Now, the interesting thing about this is that Bohr said that electrons couldn't exist between energy levels. So they can only excite or de-excite if they emit or absorb energy at specific wavelength and frequencies. But if they do obtain enough, then they don't just have to jump one energy level. They could jump by 1, they could jump by 2, or they could jump by 3 energy levels, up to an empty energy level or shell. During de-excitement, they can also drop down energy levels, but again, they don't have to drop down just by 1. The more energy levels that the electron jumps, the more levels it can drop when it de-excites. In theory, if it had excited by 3 energy levels higher than it should be, it could drop down by 1, emitting a small amount of energy of what it's absorbed. It could drop down by 2, or it could drop down right back down to the third energy level that it started from, and emit the entire amount of energy absorbed all at once. Each different change in energy level produces a different wavelength of light, and this explains why different atoms glow with different colors. So a couple more questions. Describing the Bohr model of the atom, which we've already started doing, how it's different from the Rutherford model, and what evidence he was trying to explain when he developed the model. Bohr model of the atom is a small nucleus containing protons and neutrons surrounded by electrons in a number of set orbits. In the Rutherford model, the electrons are orbiting the nucleus, but the model doesn't say there's only a limited number of orbits that the electrons can occupy. Rutherford also didn't know about neutrons, but the key idea here is literally the nature of the orbits. Finally, Bohr was trying to explain the observations that different elements absorb and emit light of only a few specific wavelengths when he came up with this idea of electron energy levels. And that meets our second criteria, explain that electrons change in orbit when there's absorption or emission of electromagnetic radiation. Finally, describe how ionization occurs. Now, this also links back in. You'll have heard the term ionization in chemistry, and you'll have heard about ionization in biology when you're talking about cellular damage, and possibly even in your physics when you're talking about the dangers of ionizing radiation. Sometimes an atom gains so much energy that one or more of the electrons can escape from the atom altogether. An atom that has lost or gained electrons is called an ion. Radiation that causes electrons to escape then is called ionizing radiation. So here we have a diagram for the ionization of a lithium atom. Lithium is in group 1 of the periodic table, which means it has one electron in its outer shell. We can see that here on the diagram. And when it's ionized, it loses that one electron, meaning that that electron in the outer shell jumps out of the shell structure altogether and is lost, leaving behind an overall charge of +1, because the lithium atom now has one more positive charge in its nucleus than it does have electrons in the shells to cancel that positive charge. An atom has the same number of protons and electrons, so overall it has no charge. If it loses an electron, then it has one more proton than it has electrons, or however many it's lost. It then has an overall positive charge and is called a positive ion. So what's going on then? Well, actually, if we've got an incident wave, a gamma wave, for example, which carries lots and lots of energy, and it has energy at the specific frequency and wavelength required to make an electron jump from the outer shell of an atom, that electron jumps and is lost to the atom. That high input of energy gives it so much energy, it literally escapes completely from the atom. One more proton in the nucleus than electrons in the shells means that now the atom has an overall charge of +1. As you can see here, we've got 4 positives and only 3 negatives left to balance it out. Because of this, the atom's been changed into a charged ion with an overall charge of +1. This then is ionization. And that answers our final outcome, describe how ionization occurs. So I hope that was useful. I want to say thank you very much for watching and see you next time. Take care.